question is basically from an aspect of physics which we call thermodynamics. Now, the question says, explain latent heat. Now, latent heat is a form of hidden heat. Is the heat that is given off or absorbed during change of state. Remember that one of the effects of heat on matter is change from one state to another. When you continue to heat matter such as ice from some maybe let's say minus 10 degrees Celsius, now that very ice is going to continue to be heated up until the temperature increases to 0 degrees Celsius. At 0 degrees Celsius, it maintains the same temperature. Now, during that time, when it maintains this very temperature, the heat you are going to be applying is going to be used to give it energy, which is needed to convert that very ice to liquid at the same 0 degrees Celsius. So during that time, what we are applying is what? Latent heat. Now, and when this very body is going to return back to the solid state, it's going to give off this heat. And the same thing happens, and that kind of latent heat during melting is called latent heat of fusion. Now, we also have latent heat of vaporization. That one occurs at boiling point. When a liquid changes to gas at boiling point, that's when it occurs. So during that time, the heat is going to be what? Absorbed. But when the very body is changing back to liquid, the heat is going to be what? Evolved. That is why sometimes when if hot water at 100 degrees Celsius pours on your body and steam at 100 degrees Celsius pours on your body, because that very steam is going to send out that very latent heat, it feels hotter than the normal water at 100 degrees Celsius. In conclusion, when the change of state is forward, that is either from solid to liquid or liquid to gas, you need to apply latent heat. That is, latent heat is going to be absorbed, but during a backward change, that is either from gas to liquid or from liquid to solid, this heat has to be evolved, that is, it has to be given off. Now the next question says, state two factors that can affect the rate of evaporation of a liquid. You can see here I have more than two already. Now, temperature can affect the rate of evaporation of a liquid. It increases it. When the wind speed is increased, it also increases the rate of evaporation. Now, when for humidity, when the air is dry, that is, if the water content of the air is very, very low, it increases evaporation. And increase in pressure also increases evaporation. Please don't forget to subscribe to the channel. And if you need a video on thermodynamics, you can comment in the comment box and I'll be responding to that as soon as I see it. Now, B part of this very question says, explain each of the following terms. Now, what are these terms? The first one is, on a dry day, water in a clay pot is cooler than water in a plastic container. So we want to explain why this observation is like this. And also, food gets cooked in a pressure cooker faster than ordinary cooking pot. Now let us go to the first one. So the first one says, on a dry day, water in a clay pot is cooler than water in a plastic pot. The first reason is because the specific heat capacity of a clay pot is higher than that of a plastic container. Now, what do I mean by specific heat capacity? That is the heat that is needed to give it a unit temperature rise. That is the first reason. So without reason is this, that the specific heat capacity of the clay pot is higher than that of the plastic. It means that what we will need more heat to give a unit temperature rise, whether in degrees Celsius or Kelvin, to that very clay pot, and thereby the water inside is kept cool. Another reason is that the clay pot allows for evaporation. Now, evaporation on a body makes that very body to be cool. So it allows for evaporation, and as the liquid or as it allows for evaporation through its pores. Now, this evaporation makes the water inside it to be what? Cooler. And that's that. But plastic does not have pores, which should give room for evaporation. On to the second part of that question. Say, food gets cooked in a pressure cooker faster than an ordinary cooking pot. Why is this so? So this is so because in a pressure cooker, the pressure is increased, and this leads to increase in the boiling point of water. Now, and since this is the case, the water is going to be hotter when it's going to boil, and the food that is in such kind of cooker will get cooked faster than that of the ordinary cooking pot, which whose water boils at 100 degrees Celsius, and then at also at the at normal atmospheric pressure. Now, let me chip in this. If you are asked a question such as, if you take water to a very high mountain, will the boiling point of the water increase or decrease? That is, will the water boil faster or later than 100 degrees Celsius? The answer is the water will boil faster, and this is because boiling point of any substance, whether water or any other substance, is the is at the point when the pressure in the saturated vapor pressure in the very container, the very substance in a certain container equals the atmospheric pressure. And you also remember that as you climb higher and higher up a mountain, or as you are going higher above the earth surface, the pressure or atmospheric pressure decreases. So as you are going up higher, the pressure that is exerted on you due to the uh, air is gradually decreasing with height. State 2, effects of heat on matter. I have so many of them here. So like we have change in temperature. The first effect of heat on matter is the change in temperature. And then we have another one there, we have expansion. So it causes expansion in length, in width, and then in height. That is both length, area, and what? Volume. And then another one is what? Change of state. So one of the effects of heat on matter is change of state. So matter can change state. For instance, a liquid can change to gas, a solid can change to liquid also, and the process can go on and on like that. I think I have shown that to you before in this very video. Now, change in physical property, e.g., we have there density, resistance, and so on. Now, density, when temperature of a body increases, that is when you heat up a body, the density decreases, but the resistance increases. Please take note of that. Then we have thermionic emission in the case of metals, and so on.
Now let's go to number 8 or number 9D question. So the question says that um, a 40-volt electric heater is used to supply current of 12 ampere for um, for 140 1400 seconds to a body of mass 1.5 kg at the melting point of the body. Now, the body melts and its temperature rises through 60 degrees Celsius in an extra 72 seconds. Now we are asked to determine the latent heat of fusion of the body and the specific heat capacity of the body. Now, these are the two things we are asked to do. This very question is also on what? Thermodynamics. And we must be able to understand that this kind of question, we are going to make use of the fact that energy that is going to be lost by the heater, it will be what? The energy gained by that very body of mass 1.5 kg. Now, and also you should know that that during change in temperature, change of states, that is for a body to melt from solid to what? To liquid, that very body possess this amount of heat, which we call latent heat, and it is independent of of temperature, because during that time temperature does not change, so there is no temperature change during latent heat. Now, so the question says that a 40 volts, we have a 40 volt electric heater is used to supply current at 12 ampere for this is the voltage, this is what? The current. Then it's used to supply this very current for about the time is what? Is 1400 seconds to a body of mass 1.5 kg at the melting point of the body. Now, so all of this energy is what? Is going to be added to this body at the melting point. Now, at the melting point of the body, you should remember that is what we call what? Latent heat, right? At that very point, the body does not change its temperature. During melting or vaporization, there is no change in temperature, right? So at this very point, this is the amount of heat that is added. And then we also have the second part of the question. It said that but let us deal with that very first part, because that very first part will help us to solve the first question. So the first question here says that we should determine the latent heat of fusion of the very body. What's the latent heat of fusion of the very body? Now, you must know that the latent heat of fusion of the very body is going to be just ml, right? This is latent heat of fusion of the very body. But now, this latent heat of fusion, we know the mass, we don't know the length. The latent heat, specific latent heat of fusion, right? But then we are going to make use of the fact that the heat that is lost by the heater will be equal to this same heat, which we call latent heat of fusion. Latent heat of fusion is an hidden heat that can be used for change of states. When you are proceeding from solid to liquid, or from liquid to gas, you are going to absorb that heat, or you need that heat. But when a body is changing from gas to liquid, or from liquid to solid, they are going to give out latent heat. That is why steam water is hotter than ordinary water at 100 degrees Celsius. So now, this is the heat that is needed. That latent heat is the heat that is needed to convert that 1.5 kilogram of that very mass to liquid form. So what is going to happen is that the heat that is going to be lost by the heater, or the energy expended or dissipated by the heater in the heater, is going to be equal to this same latent heat. So we are going to say this. Now, what is that energy? We have that power is equal to IV, and then this power is the same thing as work over what? Time. That's time rate of doing work. So that work is what? IVT. So I'm going to say that what? That the work done by the heater is what? IVT. And now we are going to predict that what? That there was no heat lost to the environment. So we are going to say that what? H equals what? IVT. So this is how we will be able to solve that now. Now let us take this. I'm going to multiply. Okay, let's write it out. We have that H equals what? 40 times 12 times what? 1400. So let's multiply that and see what it is. We have 40 times 12 times 1400. So we are going to have 6. This is going to be 6 points. So H here is what? 6.72 times 10 raised by what? Let's see. 1, 2, 3, 4, 5, 6, 7. We have 10 raised by 5. What's the unit? Joules. So that's that. Now the next question says that the second part of that question says the body melts, right? And its temperature rises through 60 degrees Celsius in an extra 72 hours. So after the body melts, right, the temperature now rises through what? The temperature now rises through rises through 60 degrees Celsius. So I still apply this current with this very voltage for another what? 72 seconds. 72 seconds. Now 72 seconds, and what happened is that what? The temperature now rose. Temperature of the body now rose from 0 degrees Celsius to what? We don't know whether it is from 0, but we know that the temperature rise, which is what? Theta 2 minus theta 1, is what? Is 60 degrees Celsius. Now we are now asked to do what? To find the specific heat capacity of the very body. What is that specific heat capacity? Is what? Specific heat capacity. Now you are going to look at the heat gained. That heat that is needed to raise the temperature of a given mass of body is what? MC theta. Where C is what? Specific heat capacity. And specific heat capacity of a body is what? Is the quantity of heat that is needed to heat a unit mass of a body through what? A degree or Kelvin rise in what? In temperature. So divide both sides by M and theta. We have it at what? M and theta. We have it at C, which we are looking for is what? H over what? M theta. So the temperature change here is what? Is 60. And what is H? That means we have a problem. Now H here is going to be what? The further energy that is transferred, or the further heat that is transferred to what? The further heat transferred to the mass of what? 1.5 kg. So that mass, we don't write the mass. The mass is 1.5 kg. Now, so that, and what is that? What is that energy? It's still at what? IVT. So this very H equals MC theta, and it equals what? IVT. Right? So that, because the heat lost by the heater will be equal to what? The heat gained by the mass. So that's going to be what? And that IVT is now what? So we are going to put here IVT over what? M theta. Now what is this going to be? We have C. I here is what? Is still 12. V is what? 40. But the time is now what? 72. The mass of the body is 1.5 kg. Then we have that the temperature rise is what? 60 degree. We just write 60. So, and then what's the specific capacity going to be? So we are going to have what? 12 times 40 times 72 divided by 1.5 times 60. 1.1. So this gives us 384 384 joule per what? Per kilogram per Kelvin, right? Now this tells us that what? We need 384 joules of heat to raise the temperature of what? 1 kilogram of what? Of this very body by what? By 1 Kelvin. So that's that for that question. Let's go to another one now.